Well, hello there and welcome back. I have to apologize for no music today. I misplaced my phone. But our topic tonight is local linear approximations. All right, and it's not too complicated of a topic, so stick with me. And our goal is to approximate the tangent line value. And I just want to stress this is not an exact value. This is the approximation to a tangent line. And two little topics I want to keep straight here. Concavity is going to play a big deal on us when we talk about local linearization or approximating a tangent line. If the tangent line is above, implying that your graph is concave down, you have an over-approximation. If you're concave up, your tangent line is below, so you have an under-approximation. And you'll hear that throughout the video tonight. So stick with me, it's sure to be a good one. The function f is twice differentiable, with f of 3 equal 2, f prime of 3 equal 5, f double prime of 3 equal negative 4. What is the approximation of f of 2.9 using a tangent line at x equals 3? And then there's a second part, so let's just attack the first one together. They tell me it's twice differentiable, so I know I can take the derivative 2 times, that's all that's saying. At this point, f of 3 equals 2, they give me an x and a y. F prime of 3 means they give me the slope, and f double prime of 3, remember, is discussing the concavity. So it says, what is the approximation of 2.9? So again, this is not an exact value, we're just approximating it using a tangent line. So the second I see that tangent line, I'm starting with my y minus y1 equals m times x minus x1. Now, they want this specifically at x equals 3. So if my x value is 3, I simply ask myself, what's my y value? And that was given here. My y value is 2. And my slope at 3 was given here. And I'm just going to throw all that together to write the equation of the line. Once I have that line, now I can approximate anything I want. So let me stress, this is not the exact value. We're just approximating what we're going to get. So I'm just going to simply substitute now. Notice I'm not changing my x or my y or my slope. Those must remain. I'm just plugging 2.9 into my equation. So I think distributing is probably your worst move. I think you should clean up inside there first. So that gets me a negative 0.1. So I really have 5 times negative 0.1. For those of you that still have issues multiplying, pretend the decimal's not there. 5 times negative 1 is negative 5. Now move the decimal in one spot. So I get negative 0.5. And I simply just need to add 2 to that. So I've got y equals 2 plus negative 0.5 is 1.5. Alright, back to the second part of the question. It says, is this approximation greater than or less than the actual value at 2.9? So all I do is I think about what they've given me. I have this tangent line, and I need to know the concavity. That's the whole key. And if I quickly look back, they told me something about f double prime, and they told me that at 3 it's negative 4. Well, what they're implying is if my concavity is negative 4, that's strictly saying my concave down. Therefore, at 2.9, my tangent line would definitely have to be greater than. And again, what's my justification? That at f prime of 3, f double prime of 3, we are concave down. Question 2. Let f of x be a particular solution to this differential equation. Let's just recall, why is it differential equation? It's just like the word sound. It's an equation with a differential, or a derivative. And they give me this nice point, so I'm going to say to myself, that's x, that's y. Write the equation for a tangent line at x equals 1, part A here. Pretty simple. So the first thing I start with is y minus y1 equals m times x minus x1. I've got my x and my y, so I can say y minus negative 2 equals whatever my slope is times x minus 1. Now I need to get my slope. Now remember, that's what dy dx is. That is the first derivative. That is your slope. So if my x is 1 and my y is negative 2 squared, looks like I get a slope of 4. And part A is done. Now we're going to use what we wrote in part A for part B. use the tangent line to approximate 1.1. And I can't stress enough, some of you want to change these numbers. These numbers do not change. You already found x, y, and the slope. All you're doing is substituting into your x variable. So I've got y plus 2 equals 4 times 1.1 minus 1. Y plus 2 equals 4 times 0.1. Remember, just multiply those two. That makes 4 and move the decimal. That's 0.4. And I have to subtract 2. So I would say y equals negative 1.6. All right, now they're going to make us work for the second half. It says, is this approximation greater than or less than 1.1? And your only justification can be, if you want to know if your tangent line is above or below, it has to be about concavity. Now you'll notice, do they say anything about the second derivative? No, but they do give you that first derivative. So you're going to have to find the second derivative. So dy dx equals xy squared. dy dx equals xy squared. Now remember, this is the first derivative. All we're going to do is take its derivative to get our second derivative. And as I read this, it says x times y squared, so make sure you go product rule. First, 2y dy dx plus y squared times 1, of course. Substitute in what I can. Oh, son of a gun, I already forgot my points. X was 1, y was negative 2. So I know x is 1, y is negative 2. I'm going to leave my dy dx. We actually know. We found dy dx. That's how we got this slope of 4 here. Times 4 plus, that was negative 2 squared. So if I keep going, that's negative 16 plus 4 is clearly less than 0. So what does that tell me? Well, that tells me that my second derivative is negative, which implies that I am concave down. Therefore, no matter where you draw this tangent line, it will always be greater. So there you have it. Hopefully pretty simple. I got a few more for you. The function g is defined as given there. Part A, write the equation for the tangent line at x equals pi. Alright, pause it, give yourself 20 seconds, see if you can do it on your own. Alright, so my x and y were very obvious. I had to get my slope. So I'm saying it's the sine of 2 pi over 3. And here's what I'm thinking. This is actually the sine of 60. And I know the sine of 60 is radical 3 over 2. The 2 tells me that I'm in the 60 times 2 is 120 degrees, which puts me in the second quadrant where sine is positive. And lastly, I just need to square that puppy. So on top I get a 3 and on the bottom a 4. Alright, part B. Does the tangent line at pi, x equals pi, lie above or below the graph for that interval? Why or why not? Alright, well again, if you want to know where your tangent line is sitting, it's strictly based on the concavity. So you've got your first derivative, go get your second, and test her out. Pause it, try it on your own. So again, I'll just walk you what's going through my head. I started with my first derivative, and of course rewrote it, so the squared's outside. Took my second, have a nice chain rule there. And I'm just going to go through and evaluate each piece. So again, pi over 3 shouts out 60. The sine of 60 is radical 3 over 2. The 2 tells me 60 times 3 is 120, which is in the second quadrant where sine is positive. So that's that piece, times 2. Cosine of pi over 3 is the cosine of 60, which is 1/2. 2 times 60 is 120, which again puts me in the second quadrant, but cosine is negative there, times my 2/3. So as I clean that up, let's see. Those 2's cancel, those 2's cancel. I get negative radical 3 over 3. And there you go. So since my second derivative, was negative, this implies that my function is concave down, which implies that my tangent line is greater than. Alright, so let's look at a tabular piece. Let h be the function that is twice differentiable, so again you can take the derivative twice. The table gives all values at h at selected points 1 through 10, and h double prime is less than 0. So what are they implying there? Well, second derivative less than 0, concave down. All right, use the tangent line. I stop there. Y minus y1 equals m times x minus x1 at x equals 7 of h to show that h of 8 is less than 5. All right, so what are they saying? They're saying look at h, and they're saying the x value is 7. So if x is 7, I know my y value is 6. Y minus 6 equals something times x minus 7. Now if I want the slope, I'm going to look at h prime at 7, and I'll see that my slope is -1. All right, tangent line perfectly done. Now they want you to show that h of 8 is less than 5. All right, so let's substitute that 8 into our equation. Now again, I just want to note, I'm not changing this equation whatsoever. I'm just taking 8 and simply putting it into x. So y minus 6 equals -1. 8 minus 7 is 1. Y equals, that's -1 plus 6. Y equals 5. Now you might be scratching your head for a moment because they did say, show that, let's see, h of 8 is less than 5, and you're getting exactly 5 as an answer. Well, let's talk about what that means. And this is really what the tangent line approximation is about. So please sketch this in your notebook. We know our function is concave down. Okay, they told us that h double prime is less than 0. And we wrote this equation of a tangent line at 7. So let's pretend this is our point 7. And let's draw that tangent line in. Whoops, that's a horrible tangent line, but go with me on this. They want to know, and we said at 7. So at 7, I have my height right here. And the question is, at 8, show that h of 8 has to be less than 5. Now, here's what we're saying. When we plugged 8 onto our tangent line, we got exactly 5. So when I plug 8 on the tangent line, I get 5. But that's saying, because this is concave down, this is an over approximation. Therefore, the actual value right here in blue at 8 has to be less than 5 because our function is an over approximation. So let me say that one more time. When I plugged the 8 in and got 5, that's on the tangent line, not the actual function. And the tangent line is an over approximation of the actual function. Do you see how this tangent line is always over the graph? If this is 8, 5, this is definitely less than 5. So because it's an over approximation, we know that h of 8 is truly less than 5 on our function. Part B. Use the secant line, so now I should be doing AROC, average rate of change, on the graph from 3 to 10. So I'm going to stop and get my points at 3 and 10. So I've got the point 3, 5, and 10, 4, to show that h of 8 is greater than 37ths. All right, so let's start with our average rate of change formula. I'm going to go y2 minus y1 over x2 minus x1, or f of b minus f of a over b minus a. 4 minus 5, 10 minus 3, I get -1/7. All right, I'm going to write that equation of a line, and I'm just going to pick the first point. It doesn't matter which one you use. So y minus 5, I just know I have a slope of -1/7 times x minus 3. All right, it says show that h of 8 should be greater than 37ths. So I'm just going to plug in my 8 now. Uh, 8 minus 3 is 5. Whoops. So I've got y equals -7/5 plus 5, which is really 35/7, which gets me 37ths. And the question was to show that h of 8 is actually greater than 37ths. Okay, now this one's a little different, so picture this again. We know our function is concave down. And if I connect my 2 points, which were 3, 5, and 10, 4, we'll say they're here and, here and here. Where is your secant line to the graph? I would say my secant line lies below the graph. Okay, clearly it's not above the graph up here. It's definitely below this curve in between here. Okay, and again, we're talking about the points in between A and B. And where does it say that? Back in the directions. Between 3 and 10. Okay, so again, I would say that my curve lies below the graph. Therefore, if I want to approximate h of 8 is definitely going to be greater than 37ths. Okay, so really the big idea you need to get is out of this question here. So if you need to kind of go back and replay it in your head and you know, watch it a second time, let's make sure we understand that completely. All right, our last big question of the night. At the beginning of 2011, a landfill contained 1,000 tons of solid waste. Stop there for a moment. What are they telling you? That's your initial condition. Did you pick that up? When your time began in 2011, you had a waste of 1,000 tons. The increasing function W models the total amount of waste stored in the landfill. Planners estimate that W will satisfy the differential equation. Okay, so an equation with a derivative, that's basically your slope for the next 30 years. W is measured in tons, T is measured in years from the start of 2011. So watch that initial condition. All right, part A, nice and easy. Use the tangent line at the graph of W at t equals 0 to approximate the solid waste the landfill contains in the first 4 months. All right, so I'm jumping in. Y minus Y1 equals M times X minus X1. Now, if you feel better, it might be actually easier if you put the problems in terms of the variables they use. Well, our initial condition was time and waste. So I'm going to say W minus W1 equals the slope times T minus T1. Okay, time is like your X, W is like your Y. So again, I'm just putting it in terms of the problem. So at t equals 0, remember we knew the waste was 1,000. So W minus 1,000 equals something times t minus 0. Now I can easily get the slope because they gave me that equation. So the W dt is equal to 1/20th times the waste. It's 1,000 minus 600. So that's 400, and half of 400 is 200. So hopefully a nice, easy part A. And don't be afraid to put the equation in terms of the variables they give you. I think that might actually make your math easier. Part B. Find the second derivative of W in terms of W. So that means we only want to see W in our equation. So I'm not going to read any further. I'm just going to start with that. dW dt equals 1/20th W minus 600. So keep in mind, this is the first derivative, dW dt. Basically, all we need to do is take its second derivative. Now, some people are going to try product rule or something silly here. I'm just going to take this and distribute it. I'm going to say this is really W over 20 minus 600 over 20. So the second derivative is equal to, well, 1/20th W would be 1/20th dW dt, and this is just a constant. Now, it says I can only express it in terms of W, so what do you know about dW dt? Well, it's right here. This is really 1/20th times 1/20th W minus 600. So now you've expressed it strictly in terms of W. And you could clean it up just a little bit. I would probably say that's 1 over 400 times W minus 600. All right, so back to the rest of the question. Use your second derivative to determine if your answer in part A is an under or over estimate. At the time, t equals 1/3. Now, don't get too excited at the moment. You have t equals 1/3, but do you even have a t in your second derivative equation? No, you have W. So you need to figure out what the waste is when the time is 1/3. So I'm simply going to go grab this equation I have up here for waste, and I'm going to say, what is the waste when my time is 1/3? So I have W equals, that'll be 200 1/3 minus 0 is 1/3, and I have to add over that 1,000. Does that make sense? I can't plug 1/3 into here because 1/3 is time, I need waste, so I'm going back and finding what the waste is at 1/3. I'm going to say this is 200 over 3 plus 3,000 over 3. Obviously 3,000 over 3 is 1,000. That gets me, if I keep checking here, 3,200 over 3. So I've got 1 over 400 times 3,200 over 3 minus 600, which I'm going to say is 1,800 over 3. And clearly, if I do that math, I don't actually need to figure it out. I know that this chunk is going to be greater than 0, which is implying that my function is concave up, therefore my tangent line should be an under approximation. Well, that does it for us tonight. Hopefully you have a better feeling about local linearization, and we'll see you tomorrow.